This is slide number 30 and I am your presenter Asloob Mudassar. Fourier theorems. There are some theorems which are very useful and they help us in order to analyze the optical system. So Fourier theorems needed in the analysis of an optical system are presented in Cartesian coordinates, which can easily be extended to polar coordinates. These will provide necessary tools for Fourier optics analysis. So if we have any optical system, in order to simplify the analysis of such optical systems, we need some theorems which are presented here. Now number one is the linearity theorem. An input object O at x, y illuminated by a normally incident plane wave in the transmission mode is represented as a linear combination of two functions O1 at x, y and O2 at x, y, where A and B are real constants. Then the Fourier transform of the object O at xy is equal to the Fourier transform of their linear combinations, which is A into O1 at xy plus B into O2 at xy. Then you know that this linear operator will go inside the curly brackets and it will operate on the x dependent quantities. So on the right hand side we have A into the Fourier transform of O1 at x, y plus B into the Fourier transform of O2 into O2 at xy. So you have noticed that the Fourier operator can penetrate inside the curly brackets and can operate on all the quantities which are xy dependent. This is the linearity theorem. Now we have the similarity theorem. First we define that, assume that the Fourier transform of small o at x, y is equal to capital O at fx, fy. So this is what we have assumed. Then the Fourier transform of the O at ax, by is equal to 1 over ab multiplied by the original Fourier transform of the object which is capital O but at fx over a, fy over b. So you see that the Fourier transform, when you multiply x with a and y with b, then in the Fourier domain we have fx divided by a, fy divided by b, and the magnitude is also divided by ab. So we have 1 over ab multiplied by capital O at fx over a, fy over b. So this is the similarity theorem. Now let's explain this theorem a little bit. If A is greater than 1 and B is greater than 1, the input object O at ax, by will contract. So with the positive values of A and B, the object O will contract. And if A is less than 1 and B is less than 1, the input object which is O at ax, by will stretch. So when A and B are both less than 1, then you know that the object O will stretch. Otherwise, when both are greater than 1, then the object O at ax, by will contract. So let's look the Fourier object and their Fourier transform in the figure. In the first row in this figure represents the object O at ax, by, and their corresponding Fourier transform are given at the second row. So look at the picture in A. It has some width, and if you compare the picture B with picture A in the object space, then you know that we have contracted the object B in comparison with the object A. But look at their corresponding Fourier transform over here. The Fourier transform in E has stretched in comparison with the Fourier transform in figure D. Now compare the object in C with the object in B. We have stretched the object in C in comparison with the object in B. So C is a stretched version of the object in B. Now look at their corresponding Fourier transform in E and F. So you can see that when C is stretched in the space domain, then its Fourier transform F will be contracted in the Fourier domain. So a stretching in space domain will result in contracting in the Fourier domain and vice versa. Their further details are given in the next slide. The Gaussian function for, we have taken the object as the Gaussian function in the previous figure, for which a is equal to 1 in A and a is equal to 2 in B and a is equal to 0.5 in C, with all peak heights equal to 1, and the widths of these peaks and the widths of these functions, Gaussian functions, in A, B and C were respectively 40, 20 and 80. As you can see that their widths are the width in A is 40, the width in B is 20 and the width in C is 80. The corresponding Fourier transform with widths 48, 96 and 25, 24 and heights are 16, 8 and 32. So you see that if the object is stretching more, its height will decrease. For example, in E the height is 8, whereas in F the height is 32, because it is more contracted as compared with the Fourier transform in D, which is expanded, which is a stretched version of the function in A, and you can see its height is 16. The height is such that the total area under the curve is the same in both cases. So if the peak is high, the signal will be compressed. If the peak is low, as in E, the peak is 8, so the signal is expanded in that case. Now the shift theorem. If the Fourier transform of an object O at xy is equal to capital O at fx, fy, then the Fourier transform of the displaced function, that is O at x minus a, y minus b, is equal to the Fourier transform of the original object, which is capital O at fx, fy, multiplied by some phase factor, which is e to the power minus iota 2 pi fx into a plus fy into b. So you see that in this, if you set a is equal to b is equal to 0, you will see that this equation will be the same as this equation over here. So if you have an object which is displaced, its Fourier transform, the Fourier transform will remain the same, except that it is multiplied by some phase factor. So this phase factor depends upon fx as well as on fy, and also on the displacing parameters a and b. So this phase factor will be multiplied to all the frequencies in the object capital O, except that when fx is equal to 0 and fy is equal to 0, the phase factor will be 0. So the central or the 0th order frequency will remain unchanged in phase, but all the other frequencies will be multiplied by this phase factor. Note that the shift in object will result in phase shift of each Fourier frequencies by a phase factor of e to the power minus iota 2 pi within the bracket fx into a plus fy into b, but the position of the Fourier spectrum would not change. So you see that this Fourier spectrum, that is capital O, is located or is centered at fx is equal to 0 and fy is equal to 0. So the position is not going to change, but only is that the other frequencies other than the 0th order frequency will be multiplied by this phase factor. Now let's calculate the magnitude of the Fourier transform in both cases, because the magnitude has to be the same. Now we are taking the Fourier transform, we are taking the absolute square of the Fourier transform of the shifted object, that is the object A shifted to the x minus a, f minus b, and here on the right hand side I have taken the absolute square of the Fourier transform of this shifted object, which is capital O at fx, fy multiplied by e to the power minus iota 2 pi. Within the bracket we have fx into a plus fy into b. And you know that if you expand this absolute square, you have the quantity as in the first bracket, as in the first parenthesis, multiplied by its complex conjugate in the second parenthesis. So in the first parenthesis, the object is the same as in the absolute square term, that is O at fx, fy multiplied e to the power minus iota 2 pi fx into a plus fy into b, whereas in the second parenthesis we have the complex conjugate, which is O complex conjugate of capital O, but at fx, fy multiplied by the complex conjugate of the phase parameter, which is e to the power plus iota 2 pi into fx comma into fx into a plus fy into b. So you see that these exponential factors will multiply, will cancel out, and we are left with the capital O at fx comma fy multiplied by the complex conjugate of capital O at fx and y. Multiplying these two, you will get the absolute value. Absolute square of this quantity can be written as the absolute square of O at fx comma fy, and this absolute and this O capital O is nothing but the Fourier transform of small o with at x comma y, which is unshifted version of the object. So look at now let's now compare the Fourier transform, the absolute square of the Fourier transform of the shifted object on the left hand side with the Fourier transform of the unshifted object with the absolute value, with the absolute square of the Fourier transform of the unshifted object. Both are equal. So the absolute value will remain the same of the Fourier transform of the shifted and the unshifted object have the same absolute values of the Fourier transform. But if you don't take the absolute Fourier transform, what you get is that according to the similarity theorem, that the Fourier transform of the object will be multiplied by this phase factor, which we have represented as e to the power minus iota 2 pi fx into a plus fy into b. So that is the position of the Fourier transform of shifted object is the same as that of the unshifted object. Now in this analysis we have noticed that O at x comma y is centered at x is equal to 0, y is equal to 0, and the capital O at fx comma fy is centered at fx is equal to 0, fy is equal to 0. Now about the shifted object O at x minus a comma y minus b is centered at x is equal to a, y is equal to b, but its Fourier transform capital O, which is at fx comma fy is centered at the same coordinate, that is fx is equal to 0 and fy is equal to 0. So the Fourier transform, the position of the Fourier transform will remain unshifted, but only the difference is that the shifted object will be for the shifted object its Fourier transform will be multiplied by some phase factor, which we have explained earlier. Now Rayleigh's theorem, also known as Parseval theorems. So if we have the Fourier transform of a small object O at x comma y as capital O at fx comma fy, then the sum up of energies of the at the object, which is O, which is the absolute square of the object O at xy, and summed over all the space domain at the space region is equal to the energy contained in the Fourier spectrum, that is the absolute square of O at fx comma fy summed over whole Fourier domain. In words, we can state that the total energy contained in O at x comma y summed over infinite space domain is equal to the total energy contained in the Fourier transform summed over an infinite Fourier domain. Here we have, in this analysis, we have assumed that there is no absorption in the optical system. Now we have the convolution theorem, very important theorem also. If the Fourier, here we are talking about two space objects. One is O at x comma y, the other is kappa at x comma y. So these are the two space domain functions. So if the Fourier transform of object O at x comma y is equal to capital O at fx comma fy, and the Fourier transform of the kappa at xy is equal to capital K at fx comma fy, then the Fourier transform of these two functions convolving with each other, that is O at x comma y convolved with kappa at x comma y, will be equal to the Fourier transform of O at x comma y multiplied by the Fourier transform of kappa at x comma y, and their Fourier transform are represented on the right hand side, which is capital O at fx comma fy and kappa at fx comma fy. So you see that the Fourier transform of the convolution of two functions will result in the multiplication of the Fourier transform as in the middle case, and on the right hand side we have shown the multiplication of the Fourier transforms. In words, the Fourier transform of two functions convolving in space domain is equal to the product of their Fourier transform in Fourier domain. So this symbol represents the convolution. This cross symbol within the circle represents the convolution. By definition, the convolution integral can be represented as. So this is the definition of the convolution in terms of integration. So on the left hand side we have the symbolic form of the convolution. So O at PQ convolved with the kappa at PQ is equal to, so this is the symbolic form and its actual value is there in the form of the integrals. That is the double integration both from minus infinity to plus infinity. Then we have O at zeta comma eta multiplied by kappa at P minus zeta Q minus eta integrated with respect to d zeta and d eta. So see that zeta and eta are the variables of the integration. So when you sum up on these variables, you are left with the results which will depend on the P and Q. Now the inverse Fourier transform of the above two equations gives, that is, we are talking about the inverse Fourier transform of this equation over here, this equation, which is already Fourier transformed. So the Fourier transform, so the inverse Fourier transform of this equation is this: O at x comma y convolved with the kappa at x comma y is equal to the inverse Fourier transform, because we have taken the inverse Fourier transform on both sides. The inverse Fourier transform of the on the left hand side will be cancelled by its inverse Fourier transform operator, but on the right hand side we have the inverse Fourier transform operator and operating on the curly bracket which contains Fourier transform of O at x comma y with the Fourier multiplied by with the Fourier transform of kappa at x comma y, and in the final result we have written that the inverse Fourier transform of the curly bracket which contains capital O at fx comma fy multiplied by capital K at fx comma fy. The mathematical equations in the red, that is this equation, and the previous equation, that is this equation. So these two equations, so these equations in the red, the mathematical equations in the red are the statement of the convolution theorems. So this is the end of slide number 30.